Hello everyone, welcome to Chemistry Travels. Today's video is the first video from the name reaction series. So in this series, we'll be doing a lot of name reactions in organic chemistry, and the first name reaction that we are going to deal with is the Pinnacle Pinacolone Rearrangement. So in Pinnacle Pinacolone Rearrangement, it is a rearrangement reaction where conversion from Pinacol to Pinacolone occurs. So what is a Pinacol and what's a Pinacolone? Pinacol is 1,2 diols or vicinal diols having two OH groups and the adjacent carbon atoms. These Pinacols or these 1,2 diols, they are converted to carbonyl compounds. The product that is formed, the carbonyl compounds that is formed are the pinaclones. They can either be aldehydes or ketones. And this conversion takes place in the presence of mineral acids like dilute H2SO4. So here we have an example that's given here. We have a 1,2 diol here. This is a Pinacol. And in the presence of dilute H2SO4, this gets converted to a pinaclone, which is a ketone in this case. It can be in certain cases an aldehyde also, depending on all the substituents that are present. But in this case, in this example, a ketone is being formed. So this simple rearrangement is known as Pinnacle Pinacolone Rearrangement, which is the conversion of 1,2 diol to a carbonyl compound in presence of a mineral acid. Now let's look at the mechanism of this reaction. The mechanism is very simple and very easy mechanism. So here we have considered the Pinacol here. This is my starting reactant, which is the 1,2 diol. Now from the acid that I have, whether it's my dilute H2SO4 for example, from the acid I have an H+. So what happens? This H+ can take up electrons. This OH group, one of the OH group, both the OH groups have lone pair of electrons, right? Oxygen has lone pair of electrons. So one of the OH group can give this lone pairs to the H+. It can abstract the H+, forming OH2. When it takes up this H+, with the help of this lone pairs, it becomes OH2. And as a result, a positive charge would be formed on the oxygen, and hence the CO bond would be broken. These electrons would be shifted to this OH2, and that would come out as water. OH2 is H2O. So this part, after taking up this H+ with the help of these lone pairs on oxygen, it would come out as H2O. That's the first step. So once this H2O comes, the CO bond is getting broken, which means that the carbon would now get a positive charge. Once the water molecule comes out, we are getting a positively charged carbocation here. And in the next step, what happens is a 1,2 methyl shift that we have. This was our product. After the removal of water, we had this positively charged carbocation was being formed. This carbocation now undergoes a 1,2 methyl shift. That is, the adjacent carbon atom, a substituent of the adjacent carbon atom would shift its position so that this positive charge is removed, and now substitution occurs at this position. Positively charged carbon atom is here. The adjacent carbon atom's substituent would shift its position and occupy the position at this positively charged carbon atom now. So in this case, the CH3s are the substituents to this adjacent carbon atom. Therefore, one of the CH3 would shift and come to the positively charged carbon atom. And as a result, what do we get as a result of the shift? This is what we get, right? You can, as you see here, the CH3 has shifted to the other side. CH3, which was initially here, has now shifted to this side, and as a result, a positive charge is developed on this carbon atom now. Earlier it was on this carbon atom, but as a result of 1,2 methyl shift, the positive carbon atom becomes this one now. Now, since that carbon atom is positive, again there is an OH group which is attached to this carbon atom. So this oxygen will have lone pairs, and it has the ability to donate lone pairs, give away the lone pairs, forming a double bond. So in order to remove that positive charge, this oxygen which is attached to that carbon positively charged carbocation, the oxygen can donate its lone pairs. It would give its lone pairs forming a double bond. So C double bond O is being formed. So now since the oxygen gave off its electron, now oxygen would become positive. Earlier this carbon was positive. So to make that carbon neutral, oxygen would donate electrons forming a double bond here. Now as a result, the oxygen, because it gave off its lone pairs, now that would become positive. Now what happens is there is an OH, hydrogen which is attached. This OH bond would break and that H plus would come out. This electron of this bond would be given to oxygen to remove the positive charge on oxygen, and H plus would come out minus H plus, and now the final product we get is CH3, C double bond O, C, CH3, CH3, C. This part as such, because of that hydrogen left from this oxygen, now it is just C double bond O with no positive charge. Now this was our pinacolone that we had. So starting from the pinnacle, we were able to reach the pinacolone in just 3 or 4 steps. Very simple steps. Next is the migratory aptitude for this reaction, because in this reaction we know that a 1-2 shift is taking place. That is, a substituent from one of the carbon atoms gets shifted to the carbocation, right? So which group would shift faster? So if there is a hydrogen substituent, hydrogen is present, means that has a higher migratory aptitude, that has the ability to migrate far to a greater extent, and followed by the phenyl groups, the aryl groups that we're having. If any aryl groups are present, they would be having the next higher priority for migrating, followed by my R group, which is my alkyl groups, hydrogen followed by aryl groups followed by alkyl groups. This is a migratory aptitude. So which group would move faster to the carbocation? And also on my aryl group, if I have electron donating groups generally at the meta or para position, then for such groups they would have a higher migratory aptitude. But if I'm having an electron donating group at the ortho position, its migratory aptitude would be less. And when you consider electron withdrawing groups, whether the electron withdrawing groups are present at ortho, meta or para position, in all the cases, electron withdrawing groups attached to a phenyl ring would cause a decrease in their migration. The migratory aptitude would be lowered, whereas electron donating groups would generally increase the migratory aptitude if they are in the meta or para position, while at ortho position they decrease the migratory aptitude. Clear? So in general, this can be considered as a trend. That is, the electron donating groups such as the OCH3 or the CH3 groups, when they are attached to the phenyl ring, the migratory aptitude is higher, while a simple phenyl group, when hydrogen is attached and there is no other substituent, it's just hydrogen, which means that this is just a phenyl group that has a lower migratory aptitude, whereas groups such as Cl and NO2, these groups are electron withdrawing groups. So these groups have the least migratory aptitude. They cause migration of the phenyl group to a very less extent compared to the OCH3 or CH3 groups, which are having high migratory aptitude. This is in case of phenyl group rings. Now if I consider the R groups like the alkyl groups, now here my tertiary systems and my will be having the highest migratory aptitude, followed by the secondary systems, which is further followed by the primary systems, right? So now let us consider this example and understand the effect of migratory aptitude. Now here I have a pinnacle, I have taken a pinnacle, and in presence of a mineral acid H+, I have to cause the Pinnacle Pinacolone rearrangement to occur, and I should find out what the final Pinacolone product is. Now in the earlier example that we saw, the mechanism that we saw, all the substituents on both the carbon atoms were methyl. This side it was methyl, this side it was methyl, here it was methyl, and here also it was methyl. So there was no other problem as such. Both the OH groups, it was possible to cause the substitution, this H+ to attack. This carbocation could be formed on any carbon atom, any one of the carbon atoms. It did not make any difference. But in this case, yes, it would make a difference. Now if I have a if I cause the substitution, if I cause the OH groups to attach the H plus, this OH group to attack H plus, I would get one carbocation. And if I cause this OH group to attack the H plus, another carbocation would be formed. Two, they're separately different because their substituents on the carbon atoms are also different. This is where the migratory aptitude comes in. We saw that hydrogen groups have a higher migratory aptitudes in comparison to the aryl groups. So on this carbon I'm having hydrogen, and on this carbon I'm having phenyl groups, aryl groups. Now migratory aptitude for hydrogen is higher, which means that carbocation should be formed on this carbon. My first carbon with the phenyl groups, there the positive charge should be formed so that my hydrogen can migrate easily. Right, compared to these two, hydrogen can migrate easily. So next step, the second step is, once the carbocation is formed, the second step is migration of an adjacent group. Now hydrogen can migrate faster. So on this carbon atom, my positive charge should be formed so that my hydrogen can migrate easily to this carbon atom. Okay, so let's look at the mechanism. So in the first step, we have my H plus here. So the OH group on this carbon atom has lone pairs that can easily abstract this H plus, and it would form OH2 plus. As we can see here, OH2 with the positive charge is being formed. Since there is a positive charge, the CO bond would now break. The electrons would be given to oxygen, would be taken up by oxygen. And as a result, water would leave off, water would move out from the system. From the system, the OH2 group, water moves out, and a positive charge is formed. Because that OH2 group has moved out, a positive charge is formed on this carbon. The CO bond is broken and a positive charge is formed here. Now since the carbocation is formed here, now the hydrogen group, which can easily shift 1,2 hydride shift, would occur. This is a tertiary carbocation that is being formed here. Now tertiary carbocation is the most stable carbocation. We know that most stable carbocation would be formed. If the carbocation was formed in this side, this would be a primary carbocation, right? If it was formed here, instead of this position, if it was formed here, if I consider the attack on this OH, and if the carbocation was formed here, then that would be a primary carbocation. Primary carbocations are less stable, whereas tertiary carbocations are the most stable. So in terms of stability of carbocation also, I can say that the attack should take place at this carbon's OH in such a way that a positive tertiary carbocation, which is more stable, is being formed. So most stable one is this. It is being formed, and in the next step, 1,2 hydride shift occurs. That is this hydrogen atom. There are two hydrogen atoms. Any one of it can shift to this carbon. A shift would occur. The hydrogen would shift. As a result, what happens? The hydrogen has now shifted to this carbon, and since the hydrogen leaves from this carbon, what happens? A positive charge is generated on that carbon. Earlier it was on this carbon, on the first carbon, but since the hydride shift 1,2 shift had occurred, and one of the substituent got shifted to this carbon, and now the second carbon becomes positively charged. And now because it is positively charged, what happens? My oxygen OH group, which is attached to that oxygen has free lone pairs. This lone pair can be taken inward, as a result forming a double bond. A double bond becomes formed, and when a double bond, the lone pair is given to the carbon and shared by the carbon. As a result, a positive charge is generated on the oxygen now. And now since the oxygen has a positive charge, the OH bond would now break, and minus H plus would move out. This hydrogen alone would move out as minus H plus. It would move out as H plus, and hence this is a product we have. The remaining part, the oxygen's positive charge, would be gone when this bond is broken and the electrons are given to oxygen. As a result, now oxygen's positive charge would be lost, and like before, it will be having the free lone pairs as such. This is my final pinacolone that I have. Okay. So from that pinacol, we were able to get the pinacolone, and in this case, we had to look into the migratory aptitude to find out where the carbocation should be formed, so that the group having the higher migratory aptitude can have the 1,2 hydride shift in this case. Okay. Let's now consider another example, which is a cyclic system, a cyclic 1,2 diol. The earlier two examples that we saw, both of them were acyclic. Okay, now what happens if it is cyclic diols? The steps are the same, the mechanism remains the same. So we'll just solve this question. We have a cyclic diol here, a pinacol, which is a cyclic diol is taken, and in presence of H plus, one of the OH groups, oxygen, would have lone pairs that can cause the attachment of this hydrogen, giving rise to an OH2 groups. And as a result of that, the oxygen atom would now get a positive charge. Since oxygen gets a positive charge, this CO bond would be broken, the electrons would shift to oxygen. As a result, water, H2O, would come off and the carbon atom would now get a positive charge. The positive that was on oxygen is balanced by this double bond, this single bond that is shifted to oxygen, hence water comes out. Now the carbon atom, because this CO bond is broken, the carbon atom becomes positively charged. So here we are getting a secondary carbocation is being formed here. Okay, now 1,2 shift has to occur. Now, where does the shift occur from? From the substituent of the adjacent carbon atom. Which is the adjacent carbon atom? This is the adjacent carbon atom, and this is my carbocation, and this one is my adjacent carbon atom. And what is the substituent on that carbon atom? This group. This bond that we are having, this group is the substituent on this carbon atom that has to be shifted now. This group would now shift and get joined. This, instead of joining to this carbon atom, now that whole group would now get shifted to this carbocation here. And as a result, instead of a 6-membered ring, now I'll be having a 5-membered ring, because one of it, now what was joined here is shifting and the bond joining comes here. A 1,2 shift is occurring. So as a result, the 6-membered ring now reduces or shrinks to a 5-membered ring. And this group, whatever we had earlier, that would act as this OH containing carbon. This would act as a branch now to the ring, a substituent or a branch to the 5-membered ring. And since the bond, the substitution was shifted, since the substituent is lost on this carbon atom, now that carbon atom would now become positively charged. When that becomes positively charged, what is the next step? The oxygen group attached to that carbon has the ability to give its lone pair of electrons. The lone pair of electrons move in. As a result, what happens? The double bond is being formed and the positive charge on the carbon atom is lost. But a positive charge is being formed on the oxygen atom. Now, to remove that positive charge, what happens? This OH bond would break. This bond would be given here and minus H plus. H plus would move out and what we have is just the carbonyl group. So, now this is an aldehyde group that we have, which is a 5-membered pentane ring with a cyclopentane with an aldehyde group as an attachment. From a 6-member, in ring cases, from a 6-membered ring, the ring got shrinked as a result of this 1,2 hydride shift, and finally we are getting a 5-membered ring. This is the case of ring structures. Clear? Now, these are two questions that you can practice. One is, both of them are very simple questions. One is a cyclic system again, first one. Now, in the second one, there is a cyclic ring is also there. Now, there is other part also. Now, this question we have to take into consideration the migratory aptitude, which group would have higher migration. So, considering all that, with H2SO4, we have to do this question for using Pinnacle Pinacolone Rearrangement, and this question had appeared in JAM 2016 paper. So solve these both questions, and that's it for today. I hope you understood the concept well. Thank you so much. Keep waiting for the next name reaction.